Greetings, my pre-calculus students. We're going to start talking about proofs. I know that might freak some of you guys out a little bit here, but it's really not that bad. Specifically, the proofs we're going to talk about are called trig identities. If you have your little pre-cal Bibles that I gave you or your trig Bibles that I gave you, it is certainly worth your time to write down. I'm going to give you a list of identities today, and then each week you'll get some more for each lesson. It's worth your time to write all those identities down so that you have them in one spot that you can refer to whenever you need to. First off, what is an identity? Well, basically it's an equation that is true for all variables for which every term is defined. So if there's something undefined, it does not qualify as being an identity. So an example, is the Pythagorean theorem an identity? Quick answer, no, it's not. Pythagorean theorem is true on certain occasions, specifically like a 3, 4, 5 right triangle, the optimal word being right triangle. A squared, B squared, C squared, A squared plus B squared equals C squared only works for a right angle or a right triangle. Therefore, it is not true for all values and is not an identity. Okay, so then can I give you an example of one that is? Yeah. I can give you an example of an identity of this. Remember when you're factoring, like if I take the binomial a squared minus b squared, difference of two squareds, it factors to a plus b and a minus b. Pick whatever numbers you want for a and b, so long as they're real numbers. Don't throw in imaginaries. That's going to put a problem into the mix because we're talking about them being defined, and for the field of real numbers, imaginaries are not defined. But yeah, this will be true for any real number for a and b. It works. Specifically, here's where you want to start writing in your trig Bibles. The first set of identities I want to talk to you about, and we've talked about this a little bit already, is that I can define the tangent function in terms of the sine function over the cosine function. Likewise, since the cotangent is the reciprocal of the tangent, since tangent is sine over cosine, that would make the cotangent the cosine over sine. Okay, those are the two quotient identities. Now, why would I even want to do that? Why would I want to take some nice just one function tangent and write it as sine over cosine? Why would I want to take one function or one trig one trig function and write it as more than one? Well, as we work through these, you'll kind of get the picture of why that might come in handy. And one of the things I'll tell you when you're doing trig identities, a lot of times writing stuff in terms of sines and cosines can be pretty valuable technique. Okay, second type of identity is called the reciprocal identities. There's basically 6 of those. I can write the sine as the reciprocal of the cosine, of the cosecant, excuse me. Sine is reciprocal of cosecant. Cosine is reciprocal of the secant, 1 over secant. Tangent, reciprocal or 1 over the cotangent. Cotangent, 1 over tan. Secant, 1 over cosine. And then cosecant, 1 over sine, or the reciprocal of sine of theta. Last type are the ones that are probably going to do you about the most good. They're called the Pythagorean identities. Why? Remember Pythagorean theorem is a squared plus b squared is c squared. So here I have a something squared plus a something squared equals 1, which is basically 1 squared. So most textbooks are only going to give you this one I have in number 1. Sine squared plus cosine squared is 1. 1 plus tangent squared is secant squared. And 1 plus cotangent squared is cosecant squared. So if they only give you 3 in the book, where do the others come from? Well, in all actuality, I'm going to show you when we have our Zoom meeting. They all come from strictly this one, but here's a better way to think of it. Again, this isn't your pre-cal, but it'll help. If I take the equation d equals r times t, distance equals rate times time, you probably learned it in your science classes. It's one equation, but it can be manipulated to come up with 3 different equations. So like instead of having the d isolated or by itself, I could isolate t. I could isolate t by saying t equals d over r. I could isolate r by taking d over t. So basically, out of one equation can come three. That's the basic idea with where these other ones come from. So in this particular equation, sine squared plus cosine squared equals 1. In its current form, I have the 1 isolated, or the 1 by itself. Now, I could isolate the sine squared by subtracting or moving the cosine squared over here. So I'd get sine squared as 1 minus cosine squared. Or I could isolate the cosine squared by subtracting the sine squared. So out of this one identity, sine squared plus cosine squared equals 1, which I'm going to call my love note. I'll tell you why when we have our Zoom meeting. Out of this 1, I can come up with 3 different identities. 1 plus tangent squared equals secant squared. Likewise, right now, secant squared is isolated. I could subtract tangent squared to isolate 1. I could isolate tangent squared by subtracting 1. So out of this equation number 4, I can get these other 2 identities. And then the last 3, 1 plus cotangent squared of theta equals cosecant squared of theta. Again, right now, cosecant squared is isolated. I could isolate the 1 by subtracting cotangent squared of theta, or I could isolate the cotangent squared of theta by subtracting 1, resulting in these 2. So I strongly recommend you write down all of these identities in your little pre-cal trig Bibles, or make sure they're in a place in your notebook to where, as I give you more and more of these identities, you can keep them handy. Again, it is a good idea to write down all 9 of these Pythagorean identities because they come in handy and you never know which form you may see or have, so it's worth your time. So, how do I know that they're true? How do I know these even work? So I'm going to start with the very first of the quotient identities I gave you. We said that sine over cosine equals tangent. Now to prove it, way back when we were doing sines, cosines, we talked about sine being opposite over hypotenuse, adjacent being or cosine being adjacent over hypotenuse, and then we redefined it as y over r and x over r. Recall that when you're dividing fractions, you basically multiply by the reciprocal. So y over r divided by x over r becomes y over r times r over x. The r's cancel. You get y over x, which is the same as opposite over adjacent, which is tangent. So that's where that one comes from. Similarly, you could do a proof. I'm not going to do it here because we're kind of, a little short on time. I don't want to make an hour-long video, but follow this same line of thought, putting cosine over sine, and you can figure out where the cotangent comes from also. I'm just going to take a couple of these reciprocal identities and work those with you, but certainly if you feel emboldened to, you could prove all 6. Again, I'm going to use x's, y's, and r's, my components of a right triangle, of a reference triangle here. Again, I know that sine is y over r, so 1 over sine is 1 over y over r. Again, I keep the top, the 1, and multiply by the reciprocal. 1 times r over y becomes r over y, which is the reciprocal of the sine, which is, in fact, the cosecant, which is what I told you in the early identities. Again, if you feel like it's your mission in life to go prove some more, here's a couple others you can play with, or you can ask me about when we have our class meeting, but that's the basic idea. Okay, let's tackle these Pythagorean identities. Specifically, my command of the English language is lacking tonight. I'm going to start with my love note, sine squared plus cosine squared. Now, we said that equals 1. You know what I'm going to do? I'm going to pull out my calculator. And let's just see if that is in fact true. You can do this on an Nspire if you want. I'm just going to do it on the 84. It'll be a little quicker to manipulate once it loads. And I'm going to go in and I'm going to type in sine of x, or sine of theta, as you will, and I'm going to square it. So that's how you write sine squared on a calculator. You can't put the little squared there. The calculator, regardless of the one you have, I don't believe that an Nspire lets you do that either. And then plus the next one, do cosine squared. I'm going to put the cosine of the angle x, and I'm going to square it. And I told you that that equals 1. Let's take a look at the graph. It appears to me I have a horizontal line that, regardless of what x is, 1, 2, 3, 4, -1, -2, it looks like it has a constant value of 1. Don't take a graph's word for it, because sometimes your eyes can deceive you, especially when it comes to graphs or pictures. I can definitely see here that regardless of what I'm picking for x, my angle, that the y value is 1. Now, that is not a proof, but rather it just kind of verifies, it kind of gives you a little peace of mind as to what's going on. If you're a more visual learner, or you like graphs, or if you're like me and Yep, so you love the unit circle, you could think of it in these perspectives. I'm going to take a unit circle, and again, by definition, a unit circle is a circle of radius 1. And if you recall that when I take a point like out here, my x coordinate is really the cosine, so this x distance is cosine, and my y coordinate, or this y distance, is the sine on your unit circle. And again, this is a reference triangle. I have a right triangle here, and I know that via the right triangle that cosine squared plus sine squared equals the hypotenuse squared, or in other words, sine squared plus cosine squared is 1. So another representation you can look at. Let's try one of these other Pythagorean identities. Let's try 1 plus tangent squared. Again, all I'm looking to show you is where it comes from. This lesson is strictly about the formulas and where they come from. We'll do some examples of actual doing proofs in part 2 of this lesson. So I have 1 plus, I know that the tangent is y over x, or opposite over adjacent, and I'm going to square that because it is tangent squared. So I square y over x, which gives me y squared over x squared. And you might ask, well, wait a minute, what happened to the 1? Well, do you see how when I squared this, it gave me a denominator of x squared? If I'm going to add these, I need to write the 1 so that it has a denominator of x squared too, the common denominator. So I just rewrote the 1 as x squared over x squared. And then that gives me x squared plus y squared over x squared. And if you recall, with your right triangle trig, that x squared plus y squared is really r squared. And r squared over x squared can be written as r over x. And r over x is just another way to write the secant function. So r over x squared is just a secant function. So when I gave you the 1 plus tangent squared theta equals secant squared, there's the proof. I'm going to go back to the calculators just for kicks here. And we'll see if this may work nicely. It may crash and burn in my face. We'll see. If it does crash and burn, it would not be the first time. So I'm going to do a little verification there. So I'm going to take, what do we have? We had 1 plus, again, to write tangent squared, I have to go in parentheses, tangent of some angle. I'm going to use x, and I'm going to square it. And we said that was equal to the secant squared. Well, the 84 does not have a secant button, but I do know that the secant is 1 over the cosine of the angle x. And yet, whenever you're doing these proofs, You need to make sure that you don't just write cosine or tangent. Each one requires an angle. And let's just compare the graphs. The blue graph will be the 1 plus the tangent squared. The red graph will be the secant squared. And they're looking pretty much the same. And likewise, if I go look at the table, regardless of the value for x, both functions are the same. So again, that does not constitute a proof. This does. Okay, let's try one more here. Let's see, we just did that one. Okay, I guess I'm going to leave that one for you to do, but follow the same kind of logic that we did here. Instead of writing your 1 as y squared over, or like, instead of having y squared over x squared and writing your 1 as x squared over x squared, I think if you write your 1 here as y squared over y squared, you'll finish, or you'll be in a lot of good position here. So I'm going to stop that as part 1, and we'll work through some examples in part 2. Thanks.